So coming to the topic, today's topic, we'll take some numericals with understanding of the equations or the correlations for the flat plate collector, or the many times it is called as liquid flat plate collector. Okay. So coming to one of the problem, here you can observe for a flat plate collector with a top loss coefficient. So top loss coefficient in the sense it is going to have both radiation and convection heat losses. So overall heat loss, if you see, it is around 6 watt per meter square degree centigrade. So that value is given from the absorber plate or the flat plate collector. The heat is going to be lost from the top. So top side with both heat losses, it is around 6.6 watt per meter square degree centigrade. The question is determine the overall loss coefficient by using following data. Now see here, overall loss coefficient for the flat plate collector, if you see by the design, we have many losses. One is the top loss, that is UT, overall loss from the top. Then bottom loss we have because of the conduction. Then at the side also we have conduction and convection losses where the air is interacting with the side surfaces. And if it is an inclined surface, at the bottom we can have both conduction as well as convection. So coming to the solution of this problem, before that they have given some details here. These are the details given in the question. So which are the blocks I have marked here in the red or blue color are the solutions. So given data is backside insulation thickness, backside in the sense bottom side thickness is 0.045 meters, okay, or the bottom thickness you can take 0.045 meters. Insulation, insulation conductivity, so that whatever the insulation is done at the bottom side, that conductivity is 0.04 watt per meter square degree centigrade. That value is given. Collector bank length, so total bank in the sense the length of the collector, if you see 8 meters it is. From the top, if you see the collector length, total collector length, 8 meter is the length. Then width is 2.5 meters. So entire collector or the screen of your mobile itself, if you see, that's the receiver or the collector. So that length is 8 meter, width is 2.5 meters for the flat plate collector. And collector thickness, the collector thickness is also given 0.08 meters. So these are the values given to find out the required details. Then edge insulation thickness. So edges are connected with the side wall, and also the tubes are connected with the flat plate collector with the bonding or some insulation material, so that no, not with the pipes and flat plate collector, sides and that insulating material. So in between that, to reduce the conduction process, they have used insulation with a thickness of 0.02 meters. So whether these values are useful or not, we'll see by the solution. Now first, before going to the equations, first we need to understand these values relates what. Okay. So coming to that part, I can show you the geometry of the flat plate collector. So here you can see this is the geometry as per the problem given: bottom losses, side losses, and the top losses. So these are the losses they are asking. See, this is the collector. From this collector, whatever the loss from the top is there, it is due to radiation here, because we assume between the glass and the absorber plate or between the glass covers also we are going to maintain some vacuum. So radiation process is going to take place, and above this glass, if you see, the air is going to be interacting. So in this uh, heat transfer process or the heat loss process between glass and atmosphere, we can consider both radiation and what are that, conduction losses, oh sorry, convection losses. So convection and radiation, both losses will be there at the top. So entirely, if you see the effective loss, it is due to combined effect of convection and radiation at the top side. I think in the heat transfer also you might have learnt about these relations where the heat losses can be found out or the heat transfer can be found out using this overall loss coefficient. So these overall loss coefficient for flat plate collectors are top, bottom, and side. Now next, coming to this topic, just a minute. I am getting a call here. Yes, am I audible?
Yes, sir.
Okay. Yeah, coming back to the discussion. So these losses, as I told, convection, radiation, all the processes, you can remember from the heat transfer subject. That is the convection heat loss from the top. So that is taking place between the plate and collector. If it is a convection process, we can use this convective heat transfer and the temperature difference. Or if it is with radiation process, we can use this using the Stefan Boltzmann constant and temperature difference with in Kelvin. So for the emissivity or the radiation losses, we have to use the temperature in Kelvin between plate and collector or the glass cover 1 raised to 4. And these are the emissivity of the plate and collectors. So depending upon these equations of radiation, temperature, all these losses of the heat from the flat plate collector are taken into consideration to find the losses or the overall loss coefficients. So overall loss coefficients to come with a clear picture. So as from this equation, you can see from the bottom, whatever the heat loss coefficient is going to take place, I can write it as heat loss from the bottom side. I can write it as UB because we may not know whether it is convection or conduction. So we can use this overall heat loss or combined loss coefficient UB. Area of the surface or the bottom surface, I can consider AS and temperature difference. So temperature difference is the temperature difference between the plate. This you have to consider the plate which is connected with tubes because we are talking about the heat transfer or the heat losses from the plate, metallic plate itself, not with the bottom insulation or not with the glasses. So keeping that in mind, we, we have to consider the temperature at which the absorber plate or the mean temperature of the absorber plate which is maintained, that is TPM, and the atmospheric temperature, so that is TA. Okay, so in place of that overall loss coefficient, we can write it as thermal conductivity of the insulation, which is given in the problem, Ki, divided by delta B. So if this is also we can consider as a overall loss coefficient at the bottom. So UB can be written as Ki by delta B. So delta B is what? Thickness of the insulation. So both values are given in the problem. I can directly substitute and get the result if they are both are in the proper units. Okay, so Ki is the insulation. So insulation value is given how much? Bottom side insulation thickness. Okay, so this is very important, bottom side or back side. And also here they have given edge. Edge is side insulations. So bottom side insulation delta B I will take 0.045 meters. So units are okay. And insulation conductivity is given K value. So Ki I can consider 0.04. So already it is in proper units, watt per meter square. I can take it as 0.04. So loss coefficient at the bottom is 0.889 watt per meter square degree centigrade. So this you can calculate and check. Then already at the top side, considering radiation and convection, they have given the answer itself, 6.6. Just a minute. Yeah, sorry for the disturbance. Yeah, now screen is visible. Hello. Just anyone can reply.
Yes, sir, visible.
Yes, sir, visible.
Okay, okay. So like that, they have considered the bottom loss coefficient. Now coming to the side losses. So side losses, what they have done? They have taken the equation for both the sides. Okay, like this. So this is the side loss. You can see the uh, absorber plate here. So this edge insulation, what they are telling, this is the insulation between the side cover and the absorber plate. So this is here visible, it is very more values, but actually seeing some small glue-like or adhesive-like material will be kept at the sides. And at the bottom, there will be huge insulation because it is having length or area more at the bottom side. The area of the plate at the side is very less. So thickness of the insulation can be changed depending upon the requirement. So at the side, if you see, the heat transfer is going to take place. Okay, if it is connected to the side cover itself directly, then it may be considered as a conduction process. And after that, from the cover, if you see, from the cover, it is having convective heat loss. Okay, convective heat loss is going to take place. But if I talk with the absorber plate and outside, so here it may be conductive. So conductivity with respect to insulation, and from side cover plate to the atmosphere, it is convection. So like this, combining both the effects, okay, on this side and other side, and at the inlet side and outlet side of these pipes. Okay, one side will be tank, it will be connected at the top of the pipes. At the bottom of the pipes, it will be again insulated. So keeping that only left and right side of these tubes, we can write it as two times both sides, left side and right side, two times L3 L1 plus L2. So as per this is L3 is the height of this insulation from the front view, and in length side you can consider L1, width we can take it as L2. Okay, so overall volume if you consider, or you can consider the one of the area of the side, L1 is the total length of the tubes is almost equal to length of the cover itself, that is L1 you can consider. L2 we can consider as width, so width in the sense the front side you can consider, and L3 is the height. So total area which is in contact with the side surfaces is two times this area into conductivity of this insulation, how much heat transfer is going through this insulation, that can be taken it as Ki, and again the temperature difference between ambient air and the plate temperature. So plate temperature we have taken as mean, so it is denoted by TPM, mean plate temperature, divided by 2 times delta S, because we are considering two sides of the cover or the two sides of the absorber plate. So after substituting or simplifying, so effectively we can, the side loss coefficient can be written as L1 plus L2 into bracket L3 Ki divided by L1 L2 into delta S. So in this equation, there is no need of temperature difference. Okay. So using this equation, one can substitute the thickness of the side insulation, length of the collector plate, width of the cover plate, and height of the cover plate. So similarly, what they have done in this problem, they have taken this equation and substituted all the values. Yes, here. So L1 is the collector bank length. Collector length is 8 meters. Then width is 2.5 meters. H or K. So if it is a convection process, they may mention in the, sorry, H they have taken, I think L3. In place of L3 in this book, they have taken H. Please make a note of this. H is the height of the collector plate. Or I think thickness. Collector thickness. See, actually thickness in the sense height they have considered here. Okay, height of the collector plate or the thickness of the collector. bottom to top, what is the thickness of the entire flat plate collector? That is 0.08 meters into conductivity of that insulation material. So side insulation material, if you see, that is, or insulation of the material conductivity is 0.04 watt per meter square degree centigrade is given. Then edge insulation thickness. So insulation for both bottom side and side insulation is same conductivity, but the thickness are different. So as I told, bottom side we need more thickness and side we can have less thickness. So L1 is length again, width into 0.02 is the thickness of the side insulation, that is delta S. So once you substitute these values, I can get side insulation. With side insulation, what is the overall loss of the heat? So that coefficient is 0.084 watt per meter square degree centigrade. Now, as per the question, we know top losses given in the question, bottom losses we have found out, side losses we have found out. Now we need to find out overall loss coefficient. So overall loss coefficient, as I told, it is the sum of all the losses. So just go on adding these values: 6.6 watt per meter square degree centigrade plus 0.889, the bottom in heat loss coefficient. Side loss coefficient is 0.084. So now once you add these all things, it is very simple. The final total or overall loss coefficient is 7.573 watt per meter square degree centigrade. So please check the answers whether they are correct or any mistakes are there. So like this we are finding the overall loss coefficient using top loss, bottom loss and side losses of the flat plate collector. Next problem is, for a collector having the following characteristics, which are the following characteristics: overall loss coefficient given in the problem 6.9 watt per meter square degree centigrade. Tube spacing. So distance between the tubes given is 120 mm. So one tube to other tube distance is 120 mm, that is tube spacing. Tube outside diameter D0 is given 15 mm. Tube inside diameter DI is given 13.5 mm. Plate thickness, absorber plate thickness is 0.4 mm. Plate material. So absorber plate is made up of copper here. Okay. So for copper, you can write in the question itself, the conductivity of the copper is 385 watt per meter degree centigrade. So this value you can take for the copper as the conductivity of the copper material. Then heat transfer coefficient inside the tubes. Heat transfer coefficient is for the inside tubes where convection will be there. So that is given 320 watt per meter square degree centigrade. So these all values are given like a characteristics of the given flat plate collector, and ignoring the bond resistance. So here in the problem, we need to ignore the bond resistance or whatever the bond is attached between the tube and the plate. Okay, so that bond resistance or the bond conductivity of the heat, we have to neglect. Whatever the losses with respect to bond is there, that we are going to neglect in this problem. Then question is, calculate the fin efficiency and collector efficiency factor. The question comes where this fin word is coming in the problem. So coming back to the concept, if you see the flat plate collector and tube, between that heat losses, I can recall these equations. Okay, here I can show you where is the bond. If the in between plate, the tubes are present, this is the bond. The blue color material, what you can see is the bond material. So that heat transfer loss because of this bonding material is neglected here. Okay, we are not considering that. And in some designs, the tubes are below the flat plate. Okay, so that bonding material, whatever is used, that is not going to affect any heat transfer. Okay, let it be. Now coming to this component, I can show you here. One more slide is there. Yes. So for this, you can analyze this pin-fin analysis. So as we are going to assume the absorber plate attached with a side cover or a side insulation, we can assume this absorber plate itself has a fin-fin, so that the equations to find out effectiveness and the efficiency of the absorber plate will be simple for us. Okay, so this plate itself is a fin. With this fin at the underside or the bottom side, the tubes will be connected with the bond, or it may be welded also. But in the problem, they have given bond material, so the tubes are attached continuously with the fin, the infinite length of the fin. With this, the tubes are connected here. Okay, so this concept is taken to analyze this flat plate collector. So as you all, I think in heat transfer they might have discussed about the pin fin. Any discussion is happened with this pin fin analysis in the heat transfer until now? Okay, for our solar subject, we'll refer only these equations, because anyhow you are learning these equations where the differential equation is considered, why this m constant value and these all equations parameters are considered. This you are going to study in heat transfer once again. So I'll just consider these equations which are important for our flat plate collector analysis. Now coming to this analysis, we are going to take the effectiveness, okay, or the efficiency of the fin. So all parameters are different here. This constant m is taken because in the equation we have this value of m. Okay, so in the efficiency of the fin equation, if you see, we have tan hyperbolic m into w minus d by 2 divided by m into w minus d by 2. So this w is the width of the collector plate. So this is w is width of the collector plate. D is either you can consider d naught or di, and many books have taken the outside diameter itself. See here, outside diameter is 15, neglecting the thickness of the tube. But in reality or the actual applications, we cannot neglect the thickness of tubes. But in formulas, they have neglected this. That is one issue or the problems with this flat plate collector, how they are going to analyze. Okay, that is one part. Now efficiency, if you see the actual definition, efficiency of the pin fin is the actual heat transfer at the pin fin to the maximum heat transfer possible from the bottom of the wall. Here you can see this is at this surface, at the vertical wall. If you see, the temperature will be very high. Heat transfer is possible maximum, or the maximum possible heat transfer from this area, that you can consider. Then actual heat transfer taking place by the pin fin. So if you take that ratio, I can call it as the efficiency of the pin fin. So how much effectively the pin fin is transferring heat, even though the wall is also having some surface area, then pin fin is also increasing some surface area. By that, we are going to find out the efficiency of the pin fin by this equation. Okay, that is tan hyperbolic of m into w minus d naught divided by 2 whole divided by m into w minus d naught divided by 2. So in this equation, clearly they have given to take d naught. But here, writing just d is very difficult. So you can remember, whenever the d comes in the efficiency or effectiveness, you can take outside diameter. The next topic is how to take this m. So m is the constant, or it is nothing but the writing the effectiveness of the pin fin with other terms. Effectiveness of the pin fin is square root of Kp by h into A. Okay, so this m is a constant. It is not effectiveness, but it is just replacement of some other terms. So just to write this equation in terms of d square theta by d square equal to m square theta, to make it on a small value, they have taken m. So that m value, if you analyze, it is multiplication of convective heat transfer coefficient H between pin fin and air. P is the perimeter of this surface, perimeter of the pin fin itself. So for small area, they have taken this perimeter. This perimeter is analyzed here or zoomed here. So for the entire pin fin, if you take, it depends on the rectangle surface, circular surface, or square surface, whatever. that perimeter they have considered, divided by conductivity material or the conductivity of this pin fin material, maybe aluminum, copper, like that. They have taken K value, and AC is area of the cross section, area of this cross section, or this area where the heat transfer is taking place through the pin fin. That is AC. So these some of the parameters are given already in the problem. So I'll find out M because M is required for finding efficiency of the fin. Next, we need to find out collector efficiency factor. So this we can define, or already I have shared in one video. There we have defined the collector efficiency factor. How to write that collector efficiency factor? You can see here. Collector efficiency factor, or one more factor is there, heat removal factor also. That may be also asked. Here you can see the collector efficiency factor. What is that collector efficiency factor F dash? It is a ratio of actual useful heat gain. See here, actual useful heat gain to the useful energy gain. Okay, that would result if the collector absorbing surface had been at the local fluid temperature. If the absorber plate or the collector plate is maintained at the local fluid temperature or the inlet temperature, then we are taking these two ratios. That is overall useful heat gain to the flat plate collector to the useful energy gain. So if you analyze these two things, the equation is 1 over W into UL whole bracket 1 divided by UL into W minus D naught 5 plus D naught. So that's why I have considered D naught here in these equations to reduce the confusions, plus delta A divided by KA D naught. Okay, so delta A is again a thickness, K is the material conductivity, D naught is the outside diameter of the pipe, plus 1 divided by pi di into HF. So now we'll see which all terms can be substituted in the given problem. So heat removal factor is not asked. So this is the heat removal factor. If with same ratio, but the temperature of the flat plate collector is considered, it is at the inlet fluid temperature. In that case, we are going to take this as heat removal factor. How much is the heat removal factor is present? Okay, coming back to this problem and equations. So as for the efficiency, we need tan hyperbolic M value. So M value I am going to find out square root of Kp divided by, square root of Hp divided by K into AC. So in this, what they have done is this Hp by AC cross section area. H is the convective heat transfer coefficient. So that is not given in the problem. So in that place, they are taking it as UL. Okay. So UL will be like Hp by AC divided by K into delta. Delta is the thickness. Okay. So that plate thickness and other values. UL is given in the problem. Overall loss coefficient 6.9 is given. So you can write by this formula also. Square root of UL by K delta. K is how much? Conductivity of the material. So conductivity of material is taken from the data handbook. So in our IA test or the exams, this conductivity can be mentioned in the problem itself. So that conductivity is given 385 for the copper. So copper conductivity is given. UL value you can take it as 6.9. If UL is not given, you can take heat transfer coefficient by convection H value into perimeter. So perimeter, if you know the collector area, surface area, if you know, I can take HP by KAC. So in that place, they have taken UL by K delta. So delta is the thickness of the plate. 0.4 mm they have given. Here they have converted into meters. So this constant M value is coming around 6.69 per meter. So taking collector, see where the width of the collector is given. So here they have taken width is 0.12 or tube spacing is 120 mm. So actually you have to consider the width of the tube depending upon the distance between tube spacing as well as the length of the material or the tube collector. So using those all values, one can find out this W value, that is 0.12 minus the outer diameter of the tubes. Outer diameter of the tubes is 15 mm. Okay, so that 15 mm divided by 2. So same ratio is taken without tan hyperbolic. So this will give us the efficiency of the fin, that is coming around 96.1% is the efficiency of the fin. So this fin is working very efficiently because the value is 96.1%. So similarly, ignoring the bond conductance. Okay, so bond conductance in this equation I have shown the bond conductance where to write 1 by Cb. Okay, or else in the earlier equations you had in between term that you can neglect. Okay, now we'll take these values 1 divided by W into UL into bracket these all terms. So as I defined earlier, so now I can just substitute the values. So W is the width of the spacing 0.12, then UL is 6.9, outer diameter is 0.015 meters. Then F value you can see here with difference. F value is the efficiency of the fin 0.961. So some books have given F value, some books have given phi value. You can substitute that. Then pi into inner diameter here. This should be very careful. Pi into inner diameter 0.0135 meters into H into Fi. So what is this H into Fi? H into Fi is nothing but heat transfer due to convection heat loss. So due to that convection heat loss, what is the heat transfer coefficient? It is 320 watt per meter square for the copper and that outside atmosphere. If you consider that value is substituted here 320, so that one can get this heat or collector efficiency factor of the flat plate collector, that is around 91.2%, or you can write it as 0.912. So here the bond conductance Cb value 1 over Cb is neglected, or as per the theory discussion you can see here in the theory the bond conductance value, yes, this is the bond conductance delta A by Ka d naught, whatever the values were there, with the outer pipe this adhesive material. Okay, this Ka and delta A is the bond. It's nothing but delta A by Ka or Ka by delta A is the Cb value. So that adhesive or bond material values are neglected. So entire middle term is neglected here. Okay. So here you can see phi value is given. It is the efficiency of the fin. Phi value. HF is the convective heat transfer coefficient of the given material with the atmosphere. So like this, the values are substituted and just found out the results. Have understood the procedure? Hello?
Yes, sir.
Okay. Now next we'll take one
Yes,
more.
sir.
Okay. Next we'll take one more problem and we'll understand what are the other equations and how these different problems are solved. Okay. So in this only we are discussing again or the theory part. The next problem is in a solar water heater, the collector plate is at 87 degrees centigrade. See here, collector plate is at 87 degrees centigrade means it is plate temperature or the mean plate temperature Tp or TPM, it is at 87 degrees centigrade. Glass cover is at 67 degrees centigrade. Okay, so the glass temperature is also given 67 degrees centigrade. Next sentence, heat from collector plate is lost to the air. So heat from collector plate is lost. Please be careful. From the plate, heat is lost to the glass. I hope you are understanding. They are not asking from the collector how much heat is lost. What they are telling, heat transfer from the collector plate is lost. From the collector plate means inside. The metal plate is going to lose the heat, is lost to the air. by convection process means here they have not mentioned any vacuum. They have taken air itself between the glass and absorber plate. If it is vacuum, then the collector efficiency will be very high. So that maintaining a vacuum is also very difficult. That's why nowadays evacuated tubes are coming into picture. Okay, next, and to the glass. See here, heat from the collector plate lost from the plate to the air by convection and to the glass covered by radiation. Okay, so here what they are telling, from plate to glass cover they are considering convection, from the glass cover to outside radiation. It is lost. If the heat transfer coefficient by convection is 4.6 watt per meter square Kelvin, so from the plate to the air, whatever the heat transfer coefficient by convection is there, it is given 4.6 watt per meter square Kelvin. Find the heat loss from the collector plate per hour per meter square surface area. So what is our requirement? We need to find out heat loss from the collector, okay, by radiation as well as convection, because in the problem itself they have mentioned between plate to cover it is convection, from cover to the outside air it is radiation. So both the processes are taking place. Also find the equivalent radiation heat transfer coefficient. So radiation heat transfer coefficient they are not given in the problem, so that also we need to find out. So where the radiation is taking place? Radiation is taking place also between plate to cover or else cover to outside atmosphere. Okay, so now coming to the problem solution. So before that they have given the problem. Take emissivity of the plate as 0.2, emissivity of the glass cover as 0.3, and F12 is 1. So here F12 is what? F12 is the efficiency, or can take it as a effectiveness. It's almost 1. Okay, so now coming to the heat transfer coefficient because of the radiation process, what we can do now, I can write the radiation equation using this heat transfer coefficient by radiation, that is sigma into Tp raised to 4 plus Tg raised to 4, provided sigma is the Stefan Boltzmann constant, Tp is temperature in Kelvin raised to 4, Tg is also in Kelvin raised to 4. So convert these temperatures in degree centigrade for radiation process in Kelvin and keep it as raised to 4, divided by 1 by epsilon P plus 1 by epsilon G. That's the emissivities of two surfaces, minus 1 into Tp minus Tg. So after converting this temperature into Kelvin and using the given values and Stefan Boltzmann constant, you have to remember. So substitute all the values in this main equation. So in the substitution they have made some mistakes, or complete Stefan Boltzmann constant is not written. You substitute all the exact values and check this value. Heat transfer loss due to radiation process. Then for the overall loss means from the plate we are losing the energy by both convection and radiation. So they are radiation loss coefficient and convective convective heat transfer coefficient and radiation heat transfer coefficient, HR plus HC. Area is common for both. So area of the surface or area of the cover plate. As I told, cover plate area will be high, absorber plate area will be less. But in general, we can consider both areas are same. So area at the top, surface, into bracket, temperature difference between plate and glass cover, where the heat transfer is going to take place. So taking all these values into F also can take here. Into F is the efficiency. Depending upon efficiency, heat transfer is going to take place. So that efficiency value is given 100%. So if you substitute all these heat transfer coefficient values, efficiency, area. One more thing here. See, you can see the area here. Find the how they have taken area as 1. Find the heat loss from the collector plate per hour per meter square surface area. So per meter square, you have to find out the unknown values. So per meter square means for 1 meter square area, you find the values. So that's why they have taken area as 1. into temperature difference. So temperature difference you can take in degree or Kelvin, whatever, both will be same. Then you can find out total heat loss or heat transfer. That is coming around 426.24 kilojoules per meter square hour, or can keep it in 118.4 watt per meter square. So any one of the units, better to keep it in 118.4 watt per meter square, because from start we are following these units. So watt per meter square, then we need to convert that into per hour. So to convert that, they have taken this multiplication, because watt is in joules per second. Okay, so to convert that per second, you can multiply by 3600. So 3600. Then you can check per hour, meter square, and this kilojoules. All these conversions, you may get around 426.24 value. So all of you take 1 minute, go through this problem or check the values. If any confusions are there, please ask me, or can put the message in the chat box. So heat transfer subject, in that we are going to use those same equations with some changes, because it is a flat plate collector, not a complete normal slab or a fin, or it is not like a given isotropic material. It depends on the different processes. And always we are not considering one process, convection, radiation, like that. It may be combined effect also. So reading these sentences are very important. You have to separate all the sentences and take the data. And according to the given sentence, you have to make the formulation of the problem. Okay. So important sentence is this only: heat from collector plate is lost to the air. To the air, it is losing by convection, and to the glass, it is losing by radiation. That's why both the processes are considered here. One is radiation, one more is by convection process. So using those both processes, what is the total heat lost? Shall we take the next problem? Yes, any replies until this?
Yes, sir.
No, are you all of you going through these problems? Are you understanding?
Yes, sir.
Okay. Or any such problems are already solved in the heat transfer subject?
So not yet, sir.
No, basics of heat transfer, like introduction to heat transfer, in that.
Yes, sir.
Okay.
Radiation, convection, these parts.
Okay, okay. I think you have gone through basic equations, correct?
Yes. So now they are deriving sir that long fin, short fin.
Okay, okay. So in that you will understand what is this constant m. Okay, what is this constant m in the derivation? Then you'll
Yes.
understand efficiency of the fin, how it is tan hyperbolic, and also you can understand effectiveness of the fin. So these terms you have to keep in mind.
Okay, sir.
Thank you. Okay, I think we'll take last problem and we'll complete this discussion here. A flat plate collector has an aluminum absorber plate. So earlier it was copper plate. In one problem they have given copper. Now it is given aluminum absorber plate. So that conductivity of that plate is 211 watt per meter degree centigrade. Of thickness of the plate 0.35 mm. So mm is given, you convert in meters. and an area of 1.5 meter square. Area of 1.5 meter square. So area of 1.5 meter square is given. It may be 1.5 by 1.5, correct? Or as per this meter square, you can take any length and width. That is also possible. And it has two risers, two riser tubes. Riser tube is nothing but the water heating tubes inside the flat plate. It has two riser tubes, each of diameter 0.025 meters. So this may be a effective diameter or the outer diameter, 0.025 meters. Length of the tubes being 1 meters. So collector length or the tube length is 1 meter. That's why the length of the collector tube can be taken 1 meter. And to make 1.5 meter square, you can take the width also. So effective area should be 1.5 meter square as per this length of the tube. Determine the collector efficiency factor. So just now we discussed collector efficiency factor when the plate temperature is maintained at the normal temperature of water, F dash. For this collector, we need to find out if the convective heat transfer coefficient from the inner tube surface to the water is, see here what they are asking, convective heat transfer coefficient in the tubes, in inner tube between surface to water is, if it is 50, 100 and 500 watt per meter square degree centigrade, calculate this collector efficiency factor. Then overall loss coefficient is 7.2 watt per meter square degree centigrade from this flat plate collector. So now again I can recall M value. So as in the problem they have given overall loss coefficient, I'll use this UL by K delta P. So overall loss coefficient is 7.2 divided by K is the conductivity of the aluminum absorber plate, 211 watt per meter degree centigrade, that is given. Delta P is here thickness of the plate, not the thickness of insulation. We are talking about the absorber plate itself acting like a pin fin. So that thickness is 0.35 mm. So convert that into in meters. So by this one can find out M value. Using this constant value in the efficiency of the fin, we can find out the efficiency of the fin. Okay. So efficiency of the given fin for this M value, diameter outside is given. Width of the plate. So width of the plate also you can just check. Length of the tube is this much. So according to that, width will be how much? So that width you take for 1.5 meter square unknown value. Substitute in this value. One can get efficiency. So this efficiency is required for finding this collector efficiency factor.
कल 6 बजे दिए थे फिर उसको टाइमिंग चेंज करके फिर बाद में 7:30 बजे दी
Santosh Patil. Okay. So for 50 watt per meter square degree centigrade, what is the
संडे को 2 मैच है
heat or sorry collector efficiency factor? You can find out by substituting in this formula. Okay, that will be F dash value for 50. For 100 you can calculate this. For 500 you can calculate this. So values are 0.794, 0.866,
बैटिंग का अच्छा है
0.934.
दोनों का भी
Now coming to this problem, in many books they have given different values of W for the same problem.
में था इनका सीएसए का
For the same problem if you refer, W in some books they have taken
पहले हमको किधर
114. So how they have
170 रन बनाने को
not clear
ज्ञान पड़ती थी
actually.
मगर इनके अपने
Similarly,
वाले
for
इसके
one more
सामने
problem, they have taken
170 रन बनाना पड़ता
0.125
उनको
without mentioning in the problem or without mentioning this W.
अभी फील्डिंग और ये उतना नहीं है
So in this problem, I prefer to go by width of the plate
अकेला स्कोर
using this length of the collector. Length of the tube is 1, area is given. You just find out W and check these values. Okay. So I hope this you can take it as a homework. So all of you can take this screenshot or by the recording of this video, you can check and find these values properly and by considering the proper W value, width of the plate. Okay, I think time is up. I will take the attendance by this images of this USN numbers. Okay, this will be the attendance, today's attendance. It's total, I think 13 members are present today. Yes. Okay, we'll stop the class here. Next class we'll take with the parameters affecting with this flat plate collector and how to improve the efficiency of the flat plate collector. So which all parameters are affecting the working of the flat plate collector we'll discuss, and we'll complete this chapter by the next class. Okay, thank you.
Okay, so thank you.